Hello, in this section we will discuss the principle of inclusion and exclusion and also the pigeonhole principles. These are very important principles that can be used to solve combinatorics problems. So let's see this Venn diagram. We have two sets A and B as follow. So as you see, A but not B is right here. B but not A is right here, and in the middle we have A intersect B. So what do we know? For a three disjoint set, so we have the cardinality, the number of elements within the set is A but not B, union with B but not A, if I include all of them, union with the intersection of B, A and B. This will give us the A but not B. The number of elements is just A but not B plus the number of elements of the B but not A plus the intersection. So now we have to solve for two finite sets, A and B. So we know from before that A but not B is the same as A, but you take away the intersection. So picture it now. This A but not B is the same as everything, all of A, but I'm taking away the intersection of the two. Also, B but not A is just B, but you take away the intersection again. So if we go back here and we try to substitute A but not B with this and B but not A with B, we take away A intersect B. So here is where we're gonna have A but not B, all of it, which is A union B, right? The whole thing is A union B, become as follow. So I'm gonna replace A but not B with this, and I'm gonna replace B but not A with this, and then you add the intersection. So as you see, if I take away A but not B minus and a plus, so what happened? We end up with A plus B minus the intersection of AB. So as we can see, A union B is all of A plus all of B, but because I count A and B and I count this A intersects B twice, so therefore we have to remove it once, because once I said all of A, I count A intersect B, and I said all of B, that means I count A intersect B again, so I must remove it once. Hence the name, the principle of inclusion and exclusion. So you include, then you exclude. Let's see this example. How many integers from 1 to 100 are either a multiple of 3 or a multiple of 5? So as we say, let A be the multiple of 3's, the set that all integers between 1 and 100 that are multiple of B, and let B be the set of all integers that are a multiple of 5. So how many are there in A? So you have 1 to 100. If I take 100 divided by 3, I get 33.33. That means 33 integers are multiple of 3. And so that set B, the same way, if you take 100 divided by 5, you get 20. So we have 20 are multiple of 5. So within this set A, I don't need to write all of them. I know there are 33 here and there are 20 here. So now the question, how many integers that are either multiple of 3 or multiple of 5? Either, that means the question is asking where would be A union B. As we've seen and we prove it, the principle of inclusion and exclusion tells us A union B is A plus B minus the intersection. How many in A? We know there are 33. How many in B is 20. And the intersection, let's find out. How many are multiple of 3 and 5? That means a multiple of 15. So the same way, we take 100 divided by 15. And then you're going to get about 6. So there are 6 elements here that are a multiple of 3 and 5 at the same time, or a multiple of 15. So then I would say minus 6. So if I do all of it, so we get 47. So we know that our 47 integers are either a multiple of 3 or 5, between 1 and 100. Let's see this example here. All the guests at the dinner party drink coffee or tea. 13 drink coffee, 10 drink tea, and 4 drink both coffee and tea. How many people are guests at the dinner party? And here we're assuming everybody has to drink something. So here I'm still dealing with two sets, and I'm gonna call them maybe C and T. So C, the cardinality of C is 13 and T is 10. What else do we know? We know that the intersection of C and T, people who drink tea and coffee, 4, but we don't know how many come to the party. That means how many drink either tea or coffee. So we know that the union of C and T, coffee and tea, is all people drinking coffee plus everyone drinking tea, minus the intersection of tea and coffee. So in this case, the coffee drinkers are 13, 10 for the tea drinkers, and we have 4 drink both of them, which give us 19. And this tells us that there are 19 people at this party.